Okay, now I'm live. One second, students. Sorry. So there was a small technical error. I wasn't able to go live. That's why I'm a little late. How are you all? Am I audible and visible? Please let me know quickly in the chat if I'm audible and visible. Am I audible and visible? All good? Yeah? Please start, ma'am. This chapter is tough, yeah. So I got a lot of requests when I was doing the midterm question answer sessions on rotational motion. So many people came and told me it's very tough. But today, I'll make this chapter super easy for you. Okay, so what's this whole lesson in less than 2 hours? I will make this chapter super easy for you. I have a lot of things and all materials with me. So we'll have a fun session learning about rotational motion and system of particles. Okay? Yes, are you all ready? So, if you are all ready, quickly smash that like button and send this video to all your friends so that they also join and we learn rotational motion together. Okay, so let's start. So, first thing that you need to know in this chapter is what is a rigid body. Okay, so before we look into the depth of this chapter, first thing, what is a rigid body? What is a rigid body? A rigid body is that something that is strong. Yeah, it is very strong. How much ever you hit it or how much ever force you apply to it, it won't change its shape. For example, anything strong. I have a cup here. Okay, so if I hit it or something, it will break after some time. Something strong. Okay, a rigid body is a body that does not change its shape during motion. Okay, so if you apply force to it or if you do something to it, it will not change its shape. Yeah. In physics, what do you say? What would a rigid body is? It is a body in which distance between any two points remain constant regardless of external force acting on it. What does that mean? Let's say if this is a rigid body, okay? This position and this position will be exactly the same unless and until, something happens to it. But even if something happens to it, if it's a rigid body, if it's moving, it will not change its shape. For example, your car. See, if you drive your car, will your car change shape? Will it become an aeroplane? No. That's because it is a rigid body. That's the first thing that you need to know on what is a rigid body. Now, any rigid body can have four types of motions. Okay. Any rigid body you take, it can move in four ways. First one, translational motion. Second one, rotational motion, rolling motion, precision. So precision is something that you don't need at this point. In your first PU, you don't need precision. So we will look at all the three. Okay? Yeah, we will look at all the three. What are the three different types of motion that a rigid body can have? Translational motion, rotational motion, and rolling motion. Okay, so what is translational motion? In translational motion, body just moves in a straight path. Rotational motion is it rotates and it moves. A rolling motion is when it rotates and it moves straight. We'll discuss each of this in detail. Okay, so this much is clear. A rigid body is something that does not change shape even when it moves. Any rigid body can have four kinds of motion, out of which three are important: translational, rotational, and rolling. Now, first one, translational motion. Okay, so you can quickly take a screenshot of this presentation. I will disappear from the screen, so you can quickly take a screenshot if you want to. Okay, let's continue. So, translational motion. So, translational motion is motion where a body travels in a straight line. Okay, so if this is a slope, if this is a slope and a body travels this way, it is moving down. Yeah, so all the points in the body, they move with the same velocity. In this example, you can see, let's say this is point P2. I'll take a different color, yellow. So let's say this is point P2 and this is point P1. Okay. So P1 and P2 are two random points inside this rigid body. Yeah, inside the full rigid body, I take two random points P1 and P2. P1 and P2 both will have the same velocity when it's moving down. So if the whole block is moving down with the same velocity, so every point inside the block is moving down with the same velocity. So that is translational motion. What is translational motion? Velocity at all points of the body will be the same at any instant. Okay, so as the block moves at all points, the velocity of the body is the same. That is translational motion. So in this picture, you can see a block that's moving down an inclined plane. Now, as it moves, every particle in the block shares the same velocity. Yes, and this is called translational motion. Now, if I take another point here, that will also have the same velocity. Another point here, any point I take will have the same velocity. Okay. So that's translational motion. Yeah, sorry. Next is rotational motion. What is rotational motion? So rotational motion is when something rotates about an axis. Okay. So let's say I rotate this pen like this. What is the axis? The axis is the excuse me, students. Yeah. Sorry. The axis is the central part. Okay. So let's say I hold it here and I rotate it this way. Okay. So it is rotating around an axis. So this kind of motion is called rotation motion. Okay. If something moves in a straight path, in a straight way such that the velocity at every point is the same, it's translational. If something rotates along a point, an axis, it is rotation. Okay. Now, even in rotation, what velocity is there? In translation, it is moving in a straight path. So you have normal velocity. But in rotation, you have angular velocity. Okay, what kind of velocity do you have? It rotates in an angle. So you have angular velocity. So angular velocity of all the particles are the same. In translational, normal or linear velocity of all the particles remain the same. Here, angular velocity of all the particles remain the same. So let's say this fan is rotating. Okay. This fan is rotating and let's say angular velocity is written by omega. So here, let's say it's omega 1 and here, let's say the rotation, it is omega 2. Omega is given by theta by t. What is theta? The total angle of rotation. So one full angle will be how much? 360 degree, which is 2 pi divided by time. So omega 1 and omega 2 will have the same value. Why? Because it is all rotating 360 degree. It will take the same amount of time. Okay. So whichever point on the fan you take, they will all have the same angular velocity. So that is rotation. Okay. Yeah, I'm all right, Chini. Thank you for asking. Okay. So that is rotation. Okay. Translational motion is done. Rotation is done. Next is rolling motion. So rolling motion is a mixture of translational motion and rotational motion. Okay. So for example, let's say you have a ball. This ball, I should have had a ball, but I don't have a ball. So this ball is rolling. So what is happening? If this is the axis, it's rotating. Yeah. It's also moving forward. So it's translating as well. So rolling is a combination of translational and rotational motion. So a rotating body moving forward is rolling. Okay. So let's look at this picture here. So this picture here, can you see it? I put it here. Now you can see it, right? So this ball, when it rolls down, okay. So here there's a ball that's rolling down an inclined plane. So you can see that the translational motion is there. It's moving down. Rotational motion is there because the ball is rotating. Yeah. So that is rolling. So because of translational motion, P1 and P2, the points inside the ball will have the same velocity. Because of angular rotation, P3 and P4, which are the ones around it, will also have the same velocity. So that's rotational motion. Okay. Yeah, I think I should just go away from the screen for a second so you can take a screenshot of this. Okay, done. Let's move on. Next is center of mass. What is center of mass, students? Center of mass means the center of a mass. Yeah? What is center of mass? Yeah? What is center of mass? For center of mass, let's say I have this pen. Okay? I don't know how to, but then you can, I can't balance this pen on one finger. Okay? Like this. I can't balance it if it's here. What happens? The pen will fall down. But I can balance it. I can't balance it here, but I can balance it like this. See, I can move it however I want to. Yeah. How do I do that? That's because I have held the pen at its center of mass. Okay. So that's how that's how you balance things. If you can hold something at its center of mass, that means all of the mass is concentrated at that point. So at this particular point, the mass on this side and this side, all the masses are the same. So that is why we can balance. That's called center of mass. Okay. So center of mass is a point at which all the mass is concentrated. Now for different shapes, it has different center of masses. So if you have a cylinder, the center of mass is here. Okay. If it's a cylinder, the center of mass is on the center. If it's a triangle, then how are the center of mass? You draw lines from the corners. From all three corners, you draw lines into the triangle. Wherever it meets, that's the center of mass. Now for a circle, it's the center of the circle. For a rectangle or a triangle, or a square, the point where both the diagonals meet, that's the center of mass. And what is the meaning of center of mass? Center of mass is a point where the mass is the same in all directions. So you can see on this square, in this direction, as well as this direction, this direction, this direction, in all the directions, the mass is the same. So you can balance it there. Okay. When I hold my pen like this, I can balance it because the mass on this side and this side are the same when it comes to that one point. Okay. So that is center of mass. Now, mathematically, what is center of mass? We looked at center of mass, with respect to, an example and all that. But mathematically, what is center of mass? So, center of mass, let's say, simple diagram. Okay. This is a mass M1. This is another mass M2. Okay. So, their center of mass will be at the center. Okay. So, C is the point where M1 and M2 have the same mass. So at point C, M1 and M2 are balanced. So point C is the center of mass. And point C is at a distance x from the origin O. Okay, that's all. I have two masses. The center of mass is at point C. C is at a distance x. Okay. Now the first mass is at a distance x1 to the origin. The second mass is at a distance x2 from the origin. Understood? Yes. So this is one mass M1, another mass M2. This is at a distance of x1. This is at a distance of x2. The center of mass is here. Center of mass is at a distance of x. That's all. Okay. Now let's erase all this and write down. So what will the formula for center of mass be? So center of mass is basically x. Okay. X will be. The only thing you should do is multiply the masses into their distance divided by the masses. Okay, what is the first mass? M1. How far it is to the origin? X1. Plus, what is the second mass? M2. How far it is to the origin? X2. Divided by, what are the two masses? M1 and M2. So, you just add them. That's all. That is center of mass. That is center of mass in mathematical form for a one-dimensional object. Okay? It is a point whole mass of the body is supposed to be concentrated. Yes, Chini, that's the answer. Very good. Very good. Very good. Okay? Yes. Any doubts here, students? So you have two masses. You take the center point, find out the position of the center point. That is your center of mass. My center point is at a distance x from the origin. Okay. So that is why I find out x. Any doubts here? Now that is for one dimension. When I have only a single particle, that's in one dimension. Now in two dimension, what should I take? I'll again take the same thing. I'll take two masses. Okay. So let's say I take one mass, m1. I'll take another mass, m2. Okay. Now where will the center of mass be? Any point where the mass is concentrated. So let's say this is the center of mass. Okay. So m1 is at x1, y1 coordinate, x-axis, y-axis, okay. M2 is at x2, y2 coordinate, okay. And center of mass is at capital X and capital Y coordinates. Alright, this is my figure. Now what will my formula be? Capital letter X will be what? The masses into the distance. The first mass is M1, its distance is x1 plus M2, x2 divided by M1 plus M2. Now what is the second mass? Y is equal to M1 into Y1 plus M2 Y2, the whole divided by M1 plus M2. Now if you have Z, what will you do? You'll take Z is equal to M1 Z1 plus M2 Z2 divided by M1 plus M2. That will be in three dimensions. Okay. So in two dimensions, I have to take the x-axis coordinates and the y-axis coordinates. In one dimension, only x-axis. In three dimensions, x-axis, y-axis and z-axis. Okay. Hi, JEE aspirant. How are your JEE preparations going? Okay, any doubts here, students? Anything you want to clarify? Till here it's very easy, no? Yeah? Two masses I take a common point where the masses are concentrated as the center of mass. I put them on an x-axis, y-axis, find out their coordinates. That's all. Okay? Yes? Okay. Now since center of mass is done, let's move on to the next topic, which is torque. Okay? The next topic is torque. Now, what is torque? Yes, Chini, very good. Your name is Chetin. Okay, hi Chetin. Hello. Please, all of you smash the like button. All of you quickly smash the like button. We need at least 100 likes for this video. Okay, quickly smash the like button and let's make it 35k subscribers. Quickly, all of you smash that subscriber button as well. Okay, next, torque. Torque is basically moment of force. So some of you might be wondering why you have to call it torque. Why can't I just call it force? So the difference between torque and force is that torque is turning force. Okay? Turning force. So whenever something rotates, you apply a force to something and that rotates, that's when you call it torque. Okay? So torque is called as the turning effect of the body. The best example I can give you is when you open a door. What happens? You go hold the door knob, you rotate it, you open the door. So when you're opening the door, you're applying a force and there's rotation. Okay, this motion is what? Rotation motion. Yeah. So that is torque. So torque is the rotational motion or turning effect of a body. Yeah, I remember you, Chetan. Yes. You were there in my last numerical session, right? Yeah. Okay. Now, why is torque important? Torque depends on two things. It depends on the force that you apply. It also depends on the distance where you apply the force. Okay. So, look at this example here. This is a door. Okay. Let's say this is my door. Yeah. This is the hinge. Okay. So, the door opens like this. Okay. This is where it is attached. The doorknob is usually here. So, when I open it, I open the door. But if the doorknob is here, it will be a little more difficult for me to open the door. Now, what if the doorknob is here? Will I be able to open the door? It will be very difficult for me. So, it will be easiest if I put my doorknob here. So, I can open it like this. So, that means the distance, this is where it is attached. This is the hinge. So, the distance from the hinge to the doorknob is very important. More the distance, easier it is for me to open the door. Understood? So if you have a screwdriver, yeah, if you have a screwdriver or a spanner, okay, you rotate a nail with, I'll show you. Yeah, if you have a spanner, okay, the longer the spanner, the more easier it is for you to rotate the screw. Yes, the longer the spanner, more easier it is for you to rotate the screw. Why? Because more the distance, more the torque. Torque is basically this rotating effect or the turning effect. Okay, so longer, more torque. More force, more torque. So torque depends on two things. What are the two things? Distance and force. Okay, distance and force. So torque depends on two things, R cross F. R is the distance from where it is rotating to where you are applying the force. That distance into force. Okay. So the more away you go from the turning point, which is usually called the pivot. Okay. Pivot is the point where the rotation happens. So more the distance from the pivot, easier it is to rotate. Okay. Now there are two kinds of torques. There are two kinds of torques. They're called anti-clockwise torque, which is positive, and clockwise torque, which is negative. Okay. Anti-clockwise torque is when the movement is in the anti-clockwise direction. Clockwise torque is when the movement is in the clockwise direction. Okay. Now let's look at this example here. You're applying a force on the spanner. Okay. So when you're applying the force, what happens? The spanner is moving up. So is it clockwise or anti-clockwise? Quickly tell me. Clockwise or anti-clockwise. So see, imagine you apply the force at point A. Okay, on point at point A. If you apply force on point A, this is my spanner, this is the screw. Okay, it's very difficult for me to rotate. But if I apply force at point B, it's easier for me to rotate. Why? Because B is more at a bigger distance to the pivot. Pivot is the point where the rotation happens. Okay, so more the distance, easier to move. Okay? Yes. So the formula for torque or turning effect is R cross F. What does R cross F mean? Distance into the force. Okay? Any doubts here? Okay? Good, all of you. Good. Now, R cross F means what? Have I written that? Okay. So R cross F means torque is equal to R cross F, which means torque is equal to R F sine theta. Okay, it is the angle between R and F. R cross F is basically R F sine theta. So theta is the angle at which the force is applied. Okay, so students, imagine force is at this, you're holding the spanner like this. So force is at an angle. Okay. So if you take this will be cos theta, this will be sine theta. So it will be along this side. So you always take the sine theta element. And what will the unit of torque be? The unit of R is Newton, radius is meters, the unit of force is Newton. So torque is going to be Newton meter. And what will its dimension be? Its dimension will be similar to the dimension of work done. Force into displacement. Same thing here, force into radius. So it will be ml square t raised to minus 2. That will be the dimension of torque. Okay. Is that clear mathematically? Yes. Midterm finished is okay. You have end term. Okay. Even if midterm finished, it's perfectly okay. For end term, you can rock in this chapter. How's the chapter so far? Are you finding it easy? Yeah? Is it easy? If it's easy, quickly, smash that like button. Quickly smash that like button and put some fire emojis in the chat if you're finding this easy. Abhi, right now I'm not, somewhere where I can do that. Okay, but I'll definitely try next time. All right. Okay. Next one. Who are all from Mysore? Okay, Kirtana's from Mysore. Hi, Kirtana. Next is the direction of the torque. To find out the direction of the torque is very easy. You use the right hand thumb rule. Okay, so you take your thumb. Yeah, you take your thumb. Right hand. The thumb will give you the direction in which the torque happens, and the fingers curl in the direction of rotation. Okay, so if this is the screwdriver, sorry, yes, whatever you want to, no, not the screwdriver, spanner. Okay, so you are rotating in this direction. So your fingers will curl in this direction, and this will be the direction of torque. Okay, so you can quickly take a look at this. All right. So this is, what do you say? The direction of torque. Now, what should you do to find out the direction of torque? You have to point the fingers, take your right hand. Okay, all of you take your right hand, point the fingers in the direction of the position vector R. Okay, so first for every rotation, it will have an axis. Yeah, so from the axis, you should curl your fingers in the direction in which the force is going to be applied. Okay, your thumb will be in the direction of the torque. So if your thumb points out of the page, so let's say it's like this, it's usually positive. The other side it's usually negative, which is anti-clockwise. Okay, all right. So this is right hand thumb rule to find out the direction of torque. Now, what is a vector form of torque? So if to write down anything in vector form, the only thing you have to do is you have to add direction to it. Okay, you have to add some direction to it. Here, what is the direction? N cap. N cap is called the unit vector. It tells you direction. Okay, so if you have anything you want to convert to vector form, you add an n cap. So what was our formula? Torque is equal to Rf sin theta. To convert it into vector form, what did we do? We will write it as torque tau is equal to Rf sin theta with an n cap. So where tau is torque, R is the position vector or the radius, F is the magnitude of force, theta is the angle between R and F, and n is the unit vector. So students, what is so see, let's say this is the radius, okay, and this is how you apply force. Okay, so this is the angle between force and radius. So the line always close to the angle will be cos theta. The line always away will be sin theta. So see, this is the radius. This is the turning point. This is the radius. I'm applying a force like this. Okay, so I'm definitely not moving in the direction of the screwdriver or in the direction of the spanner. I am moving in the upward direction. So the force is not along cos theta, it is along sin theta. That's why here I take sin theta. Now this can also be represented as what? R cross F. What does R cross F mean? Cross product. Okay, cross product, and the direction of tau is given by right hand thumb rule. Okay, yes, any doubts here? Okay. Next, we will look at an example question where you can solve not right hand thumb rule, cross product. Okay, so to find out cross product, this is a question that you can get for your KCT as well. Okay, students, a very common question in KCT. You will get it in your PU board as well. CBSE, wherever you learn, you will have questions to solve cross product. So let's find out the cross product of this question. So the question is, I'll teach you easy method to do this. What is the torque of the force? F is equal to 4i cap minus 2j cap plus 5 cap acting at a point R, which is equal to 2i cap plus 4j cap plus k cap about the origin. Okay, so force is given to you. Force is given to you what is given? Point R, which is the distance, is given to you. So we know torque is equal to R cross F is our formula. So let's do that. So torque is equal to R cross F. So first thing, to find out cross product, you have to put it inside a matrix. So how will we do that? So torque is equal to, first row of the matrix is always I, J, K. Whatever it is, if you find A cross B or X cross Z or Z cross Y, whatever you're finding, first row is always I, J, K. Okay, so you don't have to think about that. But write down I, J and K. Then look at what is first. It's R or F. Yes, in this question, R is first. So you have to look at the terms of R. What are the numbers? 2I cap plus 4J cap plus K cap. But I, J, K we've already put. So now you can ignore I, J cap. We just have to put the numbers. Under I cap, what number will you put? 2, 4 and 1. Next is R cross F, right? So next is F. Next is F. So it will be 4I cap minus 2J cap plus 5K cap. So 4 minus 2 and 5. Okay. So torque is equal to IJK 2, 4, 1, 4 minus 2 and 5. This is my matrix. This is step 1, writing matrix. So make sure you don't mismatch. Ruin the order. Because if it's R cross F, R should be the first row, F should be the second row. Okay? Whichever number or whichever alphabet or whichever term comes first, the numbers of that one should come in the first row. Okay? R cross F, R should come in the first row. Next is solving. Okay? Solving. Let's solve. So to solve, what we should do is, first we should identify, first step is take the row and column. Wait, before that, when we solve it, torque will be equal to, okay? First we will take I cap and then the terms of I cap minus J cap and then the terms of J cap plus K cap and then the terms of K cap. This is what we will be doing, okay? I minus J plus K. Now whatever is in this bracket, I'll tell you how we'll get it, but this is the basis. I terms minus J terms plus K terms. Okay? I minus J and K. Now, Now first, to find out I terms, what we are going to do is, we are going to ignore the row and column that has I. So this is I. So this is the row and column that has I. I am going to ignore that. And I will take the rest. This is my matrix for I cap. Okay. So I ignored the row and column that had I cap and I took the matrix for I cap. So now what is the matrix? 4, 1, minus 2 and 5. Now what I will do? I will cross multiply and subtract. So what will I cross multiply? 4 into 5 minus, what are the other two terms? Minus 1 into minus 2. Okay, this is my I cap terms. 4 into 5 minus 1 into minus 2. Now, next. So that I have written it here. Okay, this much is done. We got this much. Next is minus J into whatever terms are there for J cap. How will I get the J cap terms? To get the J cap terms, I will ignore the row and column containing J cap. So this is J cap. So this is the row and the column ignoring J cap. Now what is my matrix? My matrix is 2, 1, 4 and 5. So now again I will cross multiply. So this will be 2 into 5 minus 1 into 4. So that is my second J cap. Bracket is filled now. Next is plus K cap. So for that, I will ignore the row and column containing K cap. So this is K cap. So this is the row and the column that has K cap. I will ignore the two. And what will my matrix be? 2, 4, 4 minus 2. Okay. 2, 4, 4 and minus 2. Now what will this be? Cross multiply. 2 into minus 2 minus 4 into 4. So that will come as my k cap element. So I filled this bracket, and this bracket. Okay. I hope you understood the whole thing. Now, whatever we did, we have filled the brackets and then it's just basic math. So I cap, what are the terms? 4 into 5 minus 1 into minus 2. 4 5s are what? 20 minus minus 2 will be plus 2. So it will be 22 minus j cap. Inside the brackets we have 5 into 2 which is 10 minus 4 into 1 which is 4. So 10 minus 4 plus k cap into 2 into minus 2 is minus 4 minus 4 4s are 16. So this will be what? 22 I cap minus 6 j cap minus 20 k cap. So that will be my final answer. Okay. It's very easy. Yeah. All the steps I've explained in detail. So whatever question you get, you just have to change numbers. That's all. The important rule is, students, inside the matrix, first I, J, K, and then the first column should be whatever comes first. So it's R cross F. So this should be R and then the one below should be F. Okay? Any doubts here? If you're all understanding, can you quickly put some fire emojis in the chat? Let's burn the chat down. Quickly put some fire emojis in the chat. Yes, quickly. Okay. So that's all that we need to know about torque. Now coming on to the next topic, which is moment of inertia. What is moment of inertia? See, moment of inertia is the tendency of a body to not continue what it's doing. Okay, so for example, you are sitting and scrolling on Instagram. Your mother asks you to go study. You don't want to because you will sit and scroll forever, right? So that is something that you want. You want to continue to do. So your inability to keep your phone aside and go study is moment of inertia. Just joking, okay? So moment of inertia is basically the inability of any rotating body to produce a change. Okay. So for example, Earth. Earth is rotating around the sun. Yeah. Can the Earth stop rotating? No. The Earth will always keep on rotating, even if it wants to, unless and until some external force applies on the Earth, some magical power applies on the Earth, it can never stop. Yeah. So that is inertia. The Earth can never stop rotating. So it's the inability or, the tendency of an object to continuously rotate and never stop rotating is called inertia. Okay. Yeah, it does not want to stop rotation. It wants to rotate forever. That is inertia. And inertia depends on two things. What all? It depends on mass and it also depends on the distance to the axis. So for example, let's say this is my axis, okay? And I'm rotating around my axis like this. Very fast rotating, okay? Around my axis. I have a mass of m. This is Earth, okay? This is the sun. So this is moving like this. Yeah, it's moving at a distance r. So my inertia will be the distance from the earth to the center is r, and then the mass. If I multiply the mass into the distance, I will get inertia. Okay, I is equal to m r square. Okay. Yes. You will not rotate because you are very small compared to the big earth. Okay. And you are also on inertia. You don't want to move. So how will earth move you? Yeah. Okay. So yeah, that's moment of inertia. Moment of inertia is basically what? Mass into the distance square. So it is. So if this is the axis, okay, and rotation is around this axis, and this is the mass, this mass m to the distance r will give you moment of inertia. So it is mr square. Now the unit of moment of inertia is what? Mass is kilogram, r is meter square, So kilogram meter square. Okay. Now for a point, this is mr square. If you have lots of masses, it will be MIRI square. Okay. MIRI square. That will be moment of inertia. Got it? Yes? Any doubts? Anything that you want to ask? Okay. Let's move on. So, yeah. Okay. Now, for so many particles. Okay. So, let's say this is again the axis and it's rotating. Something is rotating like this. Okay. Something is rotating like this. Okay. So, see, this is a body which has a mass here, 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 here. There, it has particles everywhere. So, when this is rotating like this, all the particles are moving. Okay. All the particles are moving. So this here, let's say mass is M1, M2, M3, M4, M5, M6. All of these are moving and they all have distance towards the axis. So this distance, let's say M1, M2, M3, so many distances, so many masses. So what will the inertia be? Inertia will be inertia of the first point, let's say this point, plus the inertia of this point, plus the inertia of this point, plus the inertia of this point, inertia of all the points. So it will be I1 plus I2 plus I3, it will go on like that. So it will be, what is I? M, the inertia of mass M1 and distance R1 plus mass M2 and distance R2 plus mass M3 and distance R3. So you will get this. Moment of inertia is how many ever masses are there? The masses into radius of each one of them together, you sum it, you will get the total inertia. Okay? Yes. So something that is rotating about an axis and it always wants to continue to rotate forever. That is moment of inertia. Okay? And if you take only one particle, the moment of inertia will be mr square. But if you take all the particles, then you have to find out the moment of inertia for each particle. Okay? Now, there are moment of inertia for different shapes. Yeah? This is something you have to by heart, okay? Very sorry, students, but you have to by heart this. But I'll tell you now fun tricks to by heart this. So you have to learn the moment of inertia for all of these bodies. First one for a ring, for sphere, for cylinder. For all of these, you have to learn moment of inertia. Okay, so let's start. We'll start with, okay, we can start from here itself. We'll start with a thin circular ring. Okay, so I have a ring here to show you all property. Today's class has property. Okay, so this is a ring. Yeah. Now, first thing, you have to look at the axis. So this is the axis, the center. Okay. So this is the axis. Along this axis, this ring is rotating. So how will it rotate? Like this. Like this. Yeah. It's rotating like this along the axis. So if a ring is rotating like this, then its moment of inertia is what? Mass of all the particles into the radius. The center, the radius. Okay. So moment of inertia of a ring is what? Of a ring is mr square. Okay. Now the same ring, what I'm going to do is I am going to flip it like this. Okay. And I take the axis of rotation as this. Okay. I take the axis of rotation as this. Now initially my ring was rotating like this. For that the moment of inertia is mr square. But now I'm going to rotate my ring like this. Okay, first it was like this. Now I'm rotating it like this. So what is my axis? My axis of rotation is this. So along this axis, when I'm rotating it, the moment of inertia becomes half of the first one. Okay, so when the axis is the diameter, when the axis is the diameter, then it's mr square by 2. If the axis is perpendicular, if it's in the center, it is mr square. Okay. Hi Mohan, welcome to the lesson. If it's If the axis is at the center for a ring, it's mr square. If the axis is along the diameter, which means it's rotating like this, it is mr square by 2. Okay? Yes? Clear? Radius is clear? Next, what is the next one? Rod. I have a rod. Again, property. Okay? For this rod, if it's rotating like this, okay, it's rotating like this. So what is the axis? This is the axis. So it's rotating like this. Yeah. So the axis, if this is the rod and this is the axis is perpendicular to the rod. Yeah. So if the axis is perpendicular to the rod, then the moment of inertia is ml square by 12. Okay, these values you have to by heart. I can derive them, but then you don't have to learn the derivation. So I'm just explaining this to you. Okay, so if this is the rod where axis of rotation is perpendicular to the rod, then moment of inertia is ml square by 12. Okay, next, again I have a property which is a disk. Next one, circular disk. Okay, so I have a circular disk with me. So for this circular disk, first I keep it like this. The center, the axis is perpendicular to the disk, so it should pass straight down through the disk. Okay, axis is perpendicular to the disk. So how is it rotating? It's rotating like this. Because axis is at the center, it should rotate with respect to the axis. So it's rotating like this. What is its moment of inertia? mr square by 2. It's the same as the diameter, the ring one. Okay. So perpendicular, this is mr square by 2. Now what happens? Axis was initially like this. Now I make the axis like this. Axis is along the diameter of the disk. So this is the axis. So what happens? This ring will rotate like this. Yeah. So first disk was rotating like this where axis was in the center. Then it was mr square by 2. If I'm rotating it like this where axis is along the diameter, then it becomes mr square by 4. Yeah. So basically it reduces by half. See here also you can see for the ring like this it was mr square. Like this it's mr square by 2. So whatever is the inertia for this one, half of that will be the inertia when the axis is along the diameter. Same thing for disk. For disk when it was rotating like this it was mr square by 2. But when I rotated it like this, half of mr square by 2 which is mr square by 4. Okay? Okay. Next one is a cylinder. Okay, I don't have a big cylinder here, but I have my water bottle which can act as a cylinder. Okay. So first one is a hollow cylinder. A hollow cylinder is a cylinder like this that is open. Okay. So for a hollow cylinder, this is the axis of rotation. Along this axis, it's rotating like this. Okay. So a hollow cylinder where the axis of the cylinder is through the cylinder, then the value is mr square. Okay. So what does this represent? This is similar to what? Is it similar to a ring or a disk? What is this similar to? A ring. Yes. This is similar to a ring that was rotating like this with this as the center. So what was the value for that? First one, mr square. Same thing for cylinder. Yeah, same thing for cylinder. A cylinder which is center of mass is this way and is rotating like this will have mr square itself, just like a ring. See, it's the same thing. For the ring also, if the axis is through the center and it's rotating like this, it's mr square. Okay. Next one is solid cylinder. Solid cylinder is a cylinder closed like this. So for a solid cylinder that's rotating like this, then axis is mr square by 2, which is similar to disk. Yeah. What does this represent? A disk that's rotating like this. What's the value for disk? Mr square by 2. So for cylinder that is closed also, it's mr square by 2. So you can associate and learn. Cylinder closed and disk. Cylinder open and ring. Okay. So you can associate those and learn the values. Okay. And then sphere. I don't have a sphere, but for a sphere, if this is a sphere and it's rotating, the axis is 2mr square by 5. Okay, it's 2mr square by 5. All these values you need to learn, students. You need to by heart all these values. Okay, so I'll show you the table. You can maybe take a screenshot and by heart all these values, because for your exam they will ask you different questions, so you need to know all the values. Okay. Hi Lohit, welcome to the lesson. Okay, any doubts here? Any doubts? Thank you, Lohit. If it's nice, please make sure you share it to all your friends. Okay? All your friends. Please send it to all your class groups, because this is a chapter that's difficult for a lot of students. And I don't want it to be difficult for anybody in Vedantu, Karnataka. Okay? So please make sure you share it with all your friends. Alright? Okay. Next. Yeah, this I've just put it here again. Yeah, for 1 mark they can ask. Next, there's a question. What are the analogues of mass and force in rotational motion? What are the analogues similar to mass and force in rotational motion? What are there? So let's say mass is m. Okay, when something is moving straight, mass is m. In moment of inertia, you can say it is similar to moment of inertia I. If force is F, it's similar to torque when something is rotating. Okay, see, if a car is going on a road, you say its mass is m. Now, but if something is rotating, you don't say its mass is m, you say it's moving with moment of inertia, which is basically mass into radius. Similarly, when you simply push someone, force is force. But when you push something and it moves in a rotational motion, then you say force is similar to torque. Okay, so just like mass is there in linear motion, moment of inertia is there in rotational motion. Force is there in linear motion, but torque is there in rotational motion. Okay. Okay. Next is a radius of gyration. Radius of gyration is something that most students find difficult, but I think it's a very easy topic. See, earlier I taught you moment of inertia for a for a ring, it's mr square. If I do it this way, it's mr square by 2. For a disk, it's mr square by 2, then mr square by 4. So many values I taught you. All that you have to by heart, okay? But I will say the moment of inertia for this disk is mk square when it rotates like this. If it rotates like this, it's also mk square. The moment of inertia for this ring, if it rotates like this, is mk square. If it rotates like this, it's also mk square. The moment of inertia for a cylinder that's hollow is also mk square. For a cylinder that's closed is also mk square. What is the meaning of that? That means I is equal to mk square is a general formula to write down moment of inertia. But for different objects, the value of k will keep on changing. Yes? So, see, for a thin ring, the value of k will be r. For a disk, value of k will be r by root 2. For a cylinder, value of k will be r by root 2. So, the value of k will keep on changing. So, k is not a constant value. K is called radius of gyration. Okay? So, k is something that changes with respect to the size and shape of the object. Understood? Yeah? So, I is equal to mk square is a general way to represent moment of inertia, where k is called the radius of gyration. It keeps changing from object to object. Alright? Now, if you want to, write it in a scientific manner, what you can write is, you can say, it is the distance from the axis of rotation of a mass point whose mass is equal to the mass of the whole body, whose moment of inertia is equal to the moment of inertia about the axis. I know you didn't understand anything. Very easy. K is what? Square root of I by m. So this I is moment of inertia of the whole body. M is moment of inertia of the whole body. Okay? And you take the square root of these two, you will get K, which is the radius of gyration. Okay? So I will quickly disappear so you can look at the whole slide. Maybe take a screenshot. Yeah? And use it as your notes. So the moment of inertia for a disk, ring or a cylinder, they can all be written as mk square. But k, which is the radius of gyration, is different for each case. Okay? Yes? Yes, yes. It's very easy. Very easy. Okay. Now, how will I find out k? Let's do an exercise. Finding out k for each of these. Okay. So, we know what is the formula for k. K is equal to square root of I by m. Okay. Now, first, for a ring that's rotating like this, what is the moment of inertia? So, this is the axis. If it's rotating like this, the moment of inertia is mr square. So, square root of mr square by m, which is basically r. Square root of r square is r. So I'll get the answer as r. Okay. Now next. So what is r? The radius of gyration for a circular ring is r. Now the radius of gyration for a circular ring that is moving like this. So its axis is along the diameter. In that case, what it will be? So k will be square root of I is what? mr square by 2, the whole divided by m. So this is basically m and m will cancel. Square root of r square by 2. So it will be r by root 2. This is the second radius of gyration. R by root 2. So an easy technique is you remove m, take the square root. Okay, so for this one, k will be what? I'll remove m, take the square root. L square by 12. So this will be L by square root of 12. Next one, k will be equal to I remove m, take the square root. So it will be r square by 2. So it will be r by square root of 2. So these are different values of k. These are all the radius of gyration. Okay. So k value keeps on changing. It is basically the square root of inertia by mass. Okay. Simple. Very easy. Alright. Yes. Done. Ma'am, break. Ma'am, break. Are you all so tired of, thinking so fast? So now I want you all to find out. We'll put a column here for K. Find out the radius of gyration for each of these. Let's do that. Okay. As homework, you should find out the radius of gyration for each of these. So radius of gyration is square root of I by m. I is given to you here as a table. So you will find out K. Okay. So all of you will work this out as homework. And I'll give you all a break because so many of you are asking for a break. We will resume back at 7:50. Okay? Yeah. So when I come back at 7:50, I want all of you to come with your friends. Yeah. You should all be there in class with your friends, not alone. Happy Diwali, Guru Raj. Guru Raj is celebrating Diwali at home. Okay. So I'll see you all in 10 minutes. Quickly go, have a break, come back with full Josh. Hello, I'm back. Are you all back? So, radius of gyration, how much would it be for each one? So, for each one, it will be mr square. So, here it will be r by root 2. Here it will be L by root 12. Here it will be R by root 2. R by 2. R. R. R by root 2. Root 2 by 5R. Okay, so this will be the next table of radius of gyration. How did I get all this? I only did square root of I by m. I substituted the values of I divided by m, found out the square root. That's all. Okay, radius of gyration is easy. Easy peasy. Hollow cylinder and ring. Yes, that's what I explained. Okay. So if you've not watched that part of the class, all that in detail with properties I have explained. Okay. So please go back and watch that part of the video. Yes, there's a lot of connection. I've explained all that. Okay. Okay. Next is angular momentum. What is angular momentum? Angular momentum is basically the cross product of position vector and momentum vector. Okay. So how do you get the position? Position is given by R. Okay. Momentum is given by P. The cross product of R and P will give you angular momentum. So if you get question, what is angular momentum? You just write it is the cross product of position vector and momentum vector. Okay. It is the cross product of position vector and momentum vector. Okay. And direction is given by right hand thumb rule. Now, what is angular momentum? Not just the physics explanation. In real life, what is angular momentum? Angular momentum tells us how much rotational motion an object can have because of its mass and its velocity. That is basically momentum. What is momentum? Mass into velocity. So if this is a fan, okay. How much rotation this fan can take because of its mass and velocity is angular momentum. Okay, how do we find it? We find it by multiplying distance from the axis and multiplying it with momentum, taking the cross product. Alright, easy? Yes. Next is a derivation. So in this chapter, very few derivations you have. First derivation is relationship between angular momentum and torque. Okay, so first derivation is the relationship between angular momentum and torque. So we know that the formula is what? The formula for angular momentum, L is R cross P. Now to find out the relationship between this and torque, we start by differentiating on both sides. Okay, so the first step is differentiating with respect to time. So I will put a d by dt here and a d by dt here. Step 1, I am putting d by dt here and d by dt on the other side. Okay. Step 1 is clear. D by dl by dt equals d by dt of r cross p. Now those who don't know how to do product rule, I'll tell you a simple trick to learn that. Okay. So let's say you and your friends are going to the staff room to collect your answer sheets. Okay. So d by dt is your answer sheet. Okay. And you are M, your friend is N. Alright. D by dt is the answer sheet. You are M, your friend is N. So the teacher says, one by one you come inside and check your answer sheet. Okay. So first you are M. So you are standing outside. You tell your friend go inside. So your friend will go inside and check the answer sheet. The answer sheet is d by dt and this is your friend. So you are outside. Your friend is checking the answer sheet. And then what happens? Plus. You go inside. Your friend stands outside. So your friend is N. Your friend stands outside. You go inside and check the answer sheet. This is cross product. Okay. So if you have m cross n, first you put m outside, differentiate n plus. Then you put n outside, differentiate m. Okay. Yes. Alright. So this is cross product. So I am going to do the same thing for r cross p. Okay. Shall I do the same thing for r cross p? So how will I write it? How will I write it for r cross p? So I will write it as dl by dt is equal to, it is r cross p. So you are r, p is your friend. So first you are decent, you stand outside. R cross, your friend is checking the answer sheet. So dp by dt plus, then you stand outside, your friend stands outside. So p cross dr by dt. Now, yeah. So this will be equal to r cross, what is change in momentum by time? Force, Newton's law, plus momentum is what? Mass times velocity. Dr by dt is also velocity. Yeah. What is velocity? Displacement by time. So dr by dt is velocity, p is mv, dp by dt is f from Newton's law. Now, v cross v is 0. That's because the angle between them will cancel out. Yeah, v cross v will be 0. So this term vanishes. So now what will we have? We will have dl by dt is equal to r cross f or dp by dt, which is equal to r cross f. Okay, is this much clear? So we have dl by dt is equal to r cross f. Now, what is dl by dt? We already know the definition of torque is what? R cross f. So can I say dl by dt is equal to torque? Yeah. See, we know dl by dt is r cross f. We also know torque is r cross f. So we write it together, dl by dt is equal to torque. So hence, the change in angular momentum is basically the torque acting on it. Okay, so I'll show you the steps of the derivation. You can quickly note them down. I don't think the steps that I wrote are required because I have typed it out very neatly. Okay, so this is the first part of the derivation. You can all quickly write it down or take a screenshot or do whatever you want. If you take a screenshot, you'll have me smiling in it. Okay, yeah. Next part is this. Okay, done. So this is the relationship between angular momentum and torque. This is an important derivation that you have in this chapter. Okay. Next is, how you can learn the parameters in rotational motion. So you might see a lot of theta, omega, alpha and all. It will be difficult for you. So you can compare them and learn them. Okay. For example, let's say you have linear displacement. We know displacement is S. You know that in Newton's laws and all, right? Yeah. Yes, Ginny, it's correct. Good. So linear displacement is what? S is equal to qt square plus half at square. That S is linear displacement. Okay, when something is moving in a straight line. Now, when something is rotating, that S is represented as theta. So angular displacement is theta. Now, when you're running in a straight line or whatever, you're moving in a straight line, linear velocity is v. But if you're rotating, the same velocity is called angular velocity and it's omega. Now, if you're accelerating, linear acceleration is what? A, but angular acceleration is alpha. Now, in linear motion, mass is m, but in angular rotational motion, mass is moment of inertia. Now, in linear motion, force is force, but when force produces turning effect, it's called torque. Linear momentum is P, angular momentum is L. Okay. In translational motion, the energy that a body has is rotational energy. In rotational motion, the energy will be kinetic energy. Okay? Yes? So this helps you compare and learn the parameters. Now I put a different table here where you have parameters, formula, symbol for both linear and angular. Okay. So this table will help you remember all the parameters. If you want to quickly revise, you can just look at this. It's like an extended table of the previous. So here you can see, let's put some numbers. So here you can see, let's say force. Force is what? F. It can be given, you can find out force by doing either MA or change in momentum by time. Now in rotational, force is given by torque. Torque is either I alpha or R cross F. So all the formulas are also involved here. Now for linear, it has kinetic energy which is half mv square. But for rotational, it has kinetic energy which is half I omega square. Okay. So all the formulas are there here. You can just compare them and learn them. Okay. So this is for your quick revisions. Okay. Next one. Law of conservation of angular momentum. How will we conserve angular momentum? Are you all ready to learn that? See, what angular momentum is equal to torque we already derived. Now we know angular momentum is equal to torque. That derivation we already did. If there is no external torque, okay, angular momentum remains constant. What does that mean? No rotation. Okay, when there's no rotation, then what is it? Then dl by dt will be 0. Now, if the differential of something is 0, that means that something is a constant. Okay, see, if I differentiate 2, I will get 0. If I differentiate 5, I will get 0. That's because a differential of a constant number is a constant. So, L is also a constant. And we already know L is what? I omega. Yes. So, if I omega is a constant, then I can say that I is equal to constant by omega. So I is proportional to 1 by omega, or omega is proportional to 1 by I. Okay. So this is the law of conservation of angular momentum. Omega is proportional to 1 by I is proportional to 1 by omega. Okay. Yes. Okay. Now, okay. So let me explain this with a very simple example. Omega and I are inversely proportional. Okay. Which means the angular rotation, the angular velocity, which is omega, is inversely proportional to inertia. Okay. It's inversely proportional to inertia. What does that mean? So let's say I'm standing like this and I'm rotating. Okay. I'm sitting, so I can't rotate now, but I'm rotating. I'll rotate with a certain speed. If I put my hands like this and I rotate, will I be moving faster or slower? You tell me. You tell me. If I hold my hands like this and rotate, or I hold my hands like this and rotate, will I move faster? In which case will I move faster? When I'm standing like this, right? Why? Because in this case, I don't have a lot of distance. In this case, my distance is more. So what happens? My moment of inertia will be more. So what happens? Angular velocity will be less. Okay? So that is why, yeah. That is why. Thank you, Guru Raj. If you felt like the explanation was nice, quickly share this video to all your class groups. Okay, because I've put in some effort to make this. And quickly send this to all your class groups. Tell them rotational motion is very easy if you learn from this video. Okay? And all of you who are watching, please subscribe to the channel. Stay tuned. We have a lot of exciting content for you. All of you quickly smash that like button. Yes? Quickly, can I have some likes? Okay. Now look at this example here. The first man, he has his gym dumbbells towards the side. The second man, he has gym dumbbells in his hand. They're both rotating. Okay. So that's the figure. Keep that in mind. Now you'll see me there. Okay. So they're both rotating. So in the left image, okay, in the left image, when he had his arms stretched out and he was holding weights, the moment of inertia is large. Why? Because I have a lot of distance here. Yeah. So the axis is here. I'm rotating like this. This is my axis. From the axis, it's my weight, or this is where I'm holding the weight, is very far. Okay. So the angular momentum L, which is IW, okay, where I is very big. So what happens? I and the angular velocity are inversely proportional. So when distance is very large, what happens? Velocity is very small. So what happens? I will rotate slowly. But if I hold it everything like this, compared to the axis, masses are very close to the axis. So I is less, so I can rotate faster. Okay? Yes? Okay? So that's what happens. See, when a cat jumps from the top of a building, it does not jump like this. It jumps like this, right? It jumps like this. Why does it jump like that? Because if it jumps like this, it will go down very fast. It will go down very fast. Angular velocity will be very high. But if it spreads out, angular velocity will reduce. So it will have a safer landing. Okay? So that's the relationship between I and omega. Okay? I hope you've understood that. I think with that, we can wind up. I will do one question and then we'll wind up the class. So this is basically rotational motion. I think I put it out in a very, very easy manner. Okay. So please let me know in the comments on how the class was. Again, if you want more class with properties and all of it. Okay. All right. So let's quickly look at a question and wind up today's class. Yeah. Okay. Next, first question. State the law of conservation of angular momentum. What is the law of conservation of angular momentum? If there's no external torque, the total angular momentum of a system remains same. Yeah. So dL by dt is equal to 0 if there's no torque. Based on law of conservation of angular momentum, how does the speed of a ballet dancer vary when? Okay. How does the speed of a ballet dancer vary when outstretched her arms and legs, when she's dancing like this? Okay. When she's dancing like this. Okay. What will happen? Yeah. So when she's dancing like this, what will happen? She has a lot of, distance. So her moment of inertia is very high. Okay. So her angular speed will be less. Now when she folds her arms and legs, moment of inertia is less, but her speed will increase. Why? Moment of inertia and angular velocity are inversely proportional. Okay. Yes. Very good, Guru Raj. Good. Super. Okay. So you are all wonderful in today's class and I hope you all enjoyed today's lesson. So I will be back with amazing lessons like this, but only if you support me. So I want you to let me know in the comments on how the class was. Quickly type down on how the class was. Okay. I would love to hear from you. I will be waiting for your comments. Okay. And if you found this class helpful, please share it to all your friends. Put it in all your class groups. Share it to all your friends. And all those who are watching this, please like the video and comment, okay, which friend of yours recommended the channel to us. So I'll have a lot of regular students. So you can say, my friend, this name recommended this class. Okay. Comment down. Yeah. So I'll see you with another video in another